A fragility function expresses the probability that a structure reaches or exceeds a given damage state as a function of ground motion intensity. Every method in this application fits the same functional form, a log-normal cumulative distribution defined by two parameters: theta, the median intensity, the level at which there is a 50% probability of exceeding the damage state, and beta, the dispersion, the logarithmic standard deviation, representing record to record and modeling uncertainty. The 6 methods differ mainly in how much dynamic analysis they require and what data they need as input. User-defined option allows user to upload existing data. Only a pushover curve available with no dynamic analysis performed. FEMA Pushover for a standard modeling uncertainty-based estimate, or SPO2 IDA for a faster, clearly flagged approximation. Dynamic time history analyses available or planned IDA, cloud analysis, or multiple stripe analysis. The choice between these 3 generally follows from how the ground motion set was already run, scaled through a full range, run once each at natural intensity, or run at fixed target levels, rather than a preference between the methods themselves. For user-defined method, import brings in a file of paired records. The importer recognizes common header names IM, SA, intensity or PGA for the intensity column, EDP, drift or demand for the demand column, and falls back to the first 2 numeric columns if no header matches. This method derives fragility directly from an already completed pushover capacity curve using the FEMA 440-style capacity spectrum approach without any additional dynamic analysis. A pushover analysis must already be run and saved before this method can be used. For each damage state, the interstory drift limit is converted to an equivalent roof displacement, then to a spectral displacement using the first mode participation factor, and finally to a median intensity capacity using the fundamental period. One simplification is worth stating plainly here. A true interstory drift ratio is defined per story, the displacement difference between 2 floors divided by that story's height. This method does not compute that directly. Instead, it treats the drift limit as if it applied uniformly across the entire building and asks what roof displacement would result if every story drifted by exactly that ratio. That is the only way to connect a story-level drift threshold to a pushover curve which only records a single roof or control node displacement rather than a full per-floor profile. It is a standard accepted simplification in the FEMA capacity spectrum approach, but it does not capture drift concentration in a single soft story, worth remembering when this method is applied to an irregular structure. Modal factor, gamma, defaults to 1.3, the first mode participation factor used in the spectral displacement conversion. Roof amplitude, phi roof, is the normalized roof modal amplitude used in that same conversion entered directly here alongside gamma. 3 dispersion sources are entered: capacity, demand, and modeling uncertainty, with defaults of 0.30, 25, and 0.20. Combined in quadrature, these produce a total dispersion of approximately 0.44, a typical value for a code-designed building. These defaults may be adjusted where a better basis exists for a specific structure. Where a damage state requires a roof displacement beyond what the pushover analysis actually tested, that result is flagged as beyond capacity rather than reported as an ordinary fit. This indicates the value is an extrapolation beyond tested behavior and should be treated accordingly, or the pushover analysis extended to a larger target displacement if that damage state is significant to the assessment. Plot options include median markers on the curve and a logarithmic scale for the intensity axis. Generate fragility curves, computes and plots all enable damage states. Export PDF report produces a complete document covering methodology, parameters, fitted results, and any beyond capacity flags. This method fits fragility curves from incremental dynamic analysis data, records incrementally scaled through a suite of intensities to collapse, using the same nonlinear time history runs produced in the application. A series of nonlinear time history analyses across different ground motions and scale factors must already be completed. Extract interstory drift ratios from time history analysis, runs populates the data table automatically from every completed run. Direction selects which drift direction serves as the demand parameter x, z, or combined, the default. It has 2 options. The first option is to select worst interstory drift ratios automatically. The second option is to add node number manually against ground motion, and the application automatically find the interstory drift ratio for the related node. Collapse drift sets the threshold. 10% by default, above which a run is treated as collapsed. A run is also treated as collapsed where the analysis failed to converge, independent of this threshold. Load spectral acceleration button extracts each run's spectral acceleration, pairing it with that run's drift as the intensity demand data point. Fitting follows the same maximum likelihood approach as user-defined, with the same moment-based fallback. One distinction applies here. A run that collapsed without producing a finite drift value is still included. Its drift is set to the collapse threshold itself, so it is correctly treated as having exceeded every damage state, rather than being excluded from the fit. Generate fragility curves fits and plots all results. Save IDA stores them for later use. Export options include PNG, Excel with the underlying per-run data, and a complete PDF report. Cloud analysis fits fragility from a suite of ground motions run once each at their own natural or lightly scaled intensity rather than through a full incremental range. A regression across the resulting cloud of intensity demand points produces the fragility directly. The prerequisite is the same as IDA, a series of completed nonlinear time history runs, one per ground motion. Direction selects which drift direction serves as the demand parameter X, Z, or combined the default. It has two options. The first option is to select worst inter-story drift ratios automatically. The second option is to add node number manually against ground motion and the application automatically find the inter-story drift ratio for the related node. Load spectral acceleration pairs each run's intensity with its drift, as in IDA. The distinction from IDA lies in the fitting approach. Rather than fitting each damage state independently by exceedance, cloud analysis fits a single power law regression across the full dataset in log space. This produces coefficients A and B describing the trend, a residual dispersion around it, and an R-squared value indicating goodness of fit. For each damage state's drift limit, theta and beta are obtained by inverting this regression at the relevant threshold. Beta here is derived purely from the regression's own residual dispersion, scaled by the fitted slope. There is no separate capacity or modeling uncertainty added on top in this method. The regression scatter is the entire basis for beta. A run that did not reach a finite drift due to collapse or exclusion is left out of the regression itself since no finite value exists to regress against. Such runs still contribute to a separate collapse fragility fitted using the same binary outcome approach as IDA, provided a genuine mix of collapsed and surviving runs exists. Generate produces the regression and the resulting fragility curves together. The regression diagnostic, the fitted trend line against the actual scatter with A, B, and R-squared reported should be reviewed before export. The PDF report for this method specifically includes that diagnostic figure, a feature unique to cloud analysis among the 6 fragility analysis types. Multiple stripe analysis occupies a middle ground between the two preceding methods. A suite of ground motions is run at several fixed target intensity levels, or stripes, for example, spectral acceleration values of 0.1 g, 0.2 g, and 0.3 g with several records at each level. This is the preferred method for critical facilities, including nuclear structures, bridges, and tall buildings, since it provides repeated observations at controlled intensity levels. The requirements follows the same pattern, nonlinear time history analyses already completed at the chosen stripe intensities. In multiple stripe analysis, data extraction is identical to the IDA method. Stripe width sets the intensity spacing between stripes. A value of 0.1 groups runs into stripes at approximately 0.1 g, 0.2 g, 0.3 g, and so on. This grouping serves display and summary purposes only. The fit itself always uses each record's actual computed intensity, not the nominal stripe value. Fitting is performed by maximum likelihood on each record's actual intensity and exceedance outcome. The same underlying statistics as IDA applied to individual records rather than stripe-grouped summaries. Multiple stripe analysis adds one additional stability check, where the maximum likelihood fit produces a non-finite result, a non-positive median, or a dispersion exceeding 3.0, indicators of an unstable fit which can occur with limited or noisy observations. The method falls back to the moment estimator and reports this explicitly as moment, MLE unstable. Collapse fragility follows the same approach as IDA, maximum likelihood where a genuine mix of outcomes exists, or a geometric mean estimate with a default dispersion of 0.4 where every run collapsed. Once curves are generated, a stripe summary table reports per stripe the number of records run, the number that collapsed, and the number exceeding each damaged state's threshold, the standard presentation for this method. Generate fragility curves fits all results, save MSA stores them for later use. Export options include the plot, the underlying per-run data, and stripe summary in Excel, and a complete PDF report. This method requires an accuracy disclosure before its mechanics are described, and that disclosure should be treated as part of the method itself, not a footnote to it. This is not the published SPO2 IDA tool developed by Vatsikos and Cornell. That tool consists of empirical regression equations calibrated against a large set of dynamic analyses. Its coefficients are not reproduced here. This method instead applies the Newmark and Hall 1982 force reduction factor relationship to convert pushover ductility capacity directly into intensity capacity, a legitimate and widely taught approximation, but a substantially simpler calculation than the published tool. For this reason, it is labeled throughout the application, and in its reports as SPO2IDA simplified. The requirement is a saved pushover bilinear idealization, with its yield displacement and yield force already computed and saved. The method centers on the force reduction factor, which relates elastic strength demand to actual yielding strength provided as a function of ductility demand and how the structure's period compares to a characteristic period. For short period, acceleration-sensitive structures, the equal energy rule applies. For longer period, displacement-sensitive structures, the equal displacement rule applies, under which force reduction factor equals ductility directly. For each damaged state, the drift limit is converted to a roof displacement, then to a required ductility using the pushover's yield displacement. The applicable R value follows from the governing rule, and the median intensity capacity follows directly from R and the pushover's yield spectral acceleration. Building height and seismic weight support these conversions. TC defaulting to 0.5 seconds. 3 dispersion values combining quadrature, following the same pattern as FEMA pushover. Beta RTR, record-to-record variability, defaults to 0.40, matching FEMA P695's standard value. Beta capacity and beta model default to 0.3 quant20, consistent with the FEMA pushover method's defaults. The same check applied in FEMA pushover is applied here, where a damaged state requires ductility beyond what the pushover curve actually demonstrated. The result is flagged as beyond SPO capacity rather than reported as an ordinary result. A collapse curve is also generated directly from the pushover's own demonstrated ultimate ductility. This result is always achievable by construction, since it reflects exactly the capacity the pushover analysis tested. Generate fragility curves computes all enabled damage states and the collapse curve. Export PDF report includes the method disclosure, a diagnostic figure identifying which branch was applied, any extrapolation warnings, and full references. 6 methods, 1 shared statistical foundation, user-defined where paired data already exists, FEMA pushover or SPO2 IDA where only a pushover curve is available, IDA, cloud analysis, or multiple stripe analysis where dynamic time history results are available, with the choice among them following from how the ground motion set was executed.